Good morning, my name is Álvaro Hernández from the University of Alcalá, and I'm going to present the work Design of a SoC Architecture for the Edge Computing of NILM Techniques. Non-intrusive load monitoring is a set of techniques aimed at the disaggregation of electricity consumption in buildings and homes. They are applied in different fields, such as the intelligent management of energy demand or the development of monitoring systems that promote and enable assisted independent living, mainly for the elderly. These techniques usually have a smart meter as a main element. This is responsible for acquiring the electrical signals of interest at the entrance of the electrical network of a home, such as voltages, currents, or powers. In these devices, the sampling frequency turns out to be a key factor in the performance of the NILM techniques, having been found in previous studies that high acquisition frequencies in the range of kHz normally improve the later load detection and identification. Nevertheless, high sampling frequencies may imply a high computational cost on behalf of the smart meter. Because of that, most commercial smart meters just upload the measurements to the cloud, where the processing is carried out. Taking into account this configuration, typical sampling frequencies are low to keep the required bandwidth also reduced. This is why this work presents a system-on-chip architecture based on an FPGA focused on the real-time implementation of NILM techniques, locally in the smart meter. Together with the FPGA mentioned before, the proposed architecture is also based on the ADE 9153 circuit, which behaves as an analog frontend. It is capable of acquiring instantaneous RMS voltages and currents, as well as powers, at a maximum frequency of 4 kilosamples per second. As can be observed in the figure, the device is managed by the SoC architecture through an SPI link at 10 MHz. Using this link, the input samples are directly sent to an advanced peripheral, which is dedicated to the detection of the on-off switching from appliances, known as events. There is also an ARM processor in the architecture in charge of the global management, which is also responsible for possible upstream communication. The following table shows the resource consumption for the different blocks of the design, including the modules from the advanced peripheral. You can observe that the figures are low in general terms, what makes feasible the possibility of integrating other peripherals that can support the processor in the load identification tasks that follow in the NILM techniques. It is also worth mentioning that the design has been specified using the Xilinx HLS tool and implemented in the smallest device of the Sync family, with a clock frequency in the programmable logic of 100 MHz. As an example, here you can see an experimental capture of the switching on and off of an electrical kettle, where it is possible to identify the slopes up and down for the different connections, particularly in the RMS current shown below. In the same way as before, here you can observe the buffer acquired for the instantaneous current and voltage for the on event of the kettle shown before. It is clear how the current becomes different from zero at the moment of the switching on. And this is all. Thank you very much for your attention.